Today I'm going to show you how to measure flicker coming from electronic devices such as laptops, phones, car dashboards, light bulbs, things like that. Because the flicker from those devices can cause headaches for many people and other symptoms as well. And so, for instance, if you're interested in buying a new phone, and maybe you have a couple phones, older phones laying around, maybe two that don't give you headaches and two that do give you headaches. You can measure the flicker of all four devices and see the pattern of the ones that give you headaches versus the ones that don't give you headaches. And then when you're evaluating a new phone, you would simply measure the flicker and see, does it look like it's going to cause me a problem based on its flickering, or do I think it'll be fine? So you can save a lot of literal headaches that way. So here we have the graphed output of the flicker of an old-fashioned incandescent light bulb. On the vertical axis, the x-axis, we have the light output of this light bulb, which you can see varies between a little bit more than 300 millivolts to a little bit under 300 millivolts. And on this horizontal axis, the x-axis, we have time. And each of these vertical lines here is 10 milliseconds. So this entire thing is 100 milliseconds, so a tenth of a second. So in that tenth of a second time, you can see that the light bulb is flickering. But it's going very gradually from this low point up to this high point, to this low point to this high point, and it's a gradual flicker. And for the vast majority of people, these old incandescent light bulbs are not going to cause headaches because of the gradual nature of this flickering. Now let's contrast that with an LED flashlight that has something called pulse width modulation, or PWM. It has a very abrupt flicker, and this is very likely to cause headaches in people who are susceptible to headaches. And so you can see that the light output is actually zero. There was probably some ambient light, but the light output is zero down here, and then it very quickly changes to over 300 millivolts and stays at that level for a time, and then drops down dramatically to zero, where it continues at that rate for some time and then shoots up. And so this very abrupt flickering, the drastic up-down nature of this flickering is likely to cause headaches in people. And I chose, and I'll just show you them side by side so you can see them one more time. So we have the very smooth gradual flicker that's unlikely to induce headaches, and we have the very abrupt flicker that for many people will induce headaches, or is very likely to induce headaches. These two examples are very extreme, and I chose them for that reason. The point is, for each individual person, their tolerance for the amount of flicker that's going to cause them headaches will vary. And so what you want to do is you want to measure all of the devices that you have and look at the flickering that's caused by it, and make determinations to say, this kind of flickering is going to be a problem and this will not for you. And so I'll show some more. I'll show, the first thing I'll do is I'll show how to create these graphs, and then I'll show some that are, in between these two extremes. In order to create these graphs, you're going to need three things. The first is a photodetector, and I have one. It's a PDA 100A2 by Thorlabs, and you can see it has a little, basically like a light detector right here, like you would imagine with a solar cell, that generates power. So a light detector. You will need an oscilloscope. I have the picoscope 224A, and I'll put a link in the description to that as well. And you will need some software that comes for free with that picoscope oscilloscope. The first thing you're going to do is assemble everything together, and I'll show you how to do that. So this cord here is just a standard one that you'd get with a like a computer monitor or a computer, and that will plug into the power supply that's going to power your light detector, your photo detector. One thing that's important about this is right here there is a voltage selector. It's hard to see, but I've got it on 120 volts because I'm here in the US. You have to make sure that that's set to the right value. So I'll plug, so this is plugged into the wall. I'll plug it into here. Simple enough. There is a power switch, but I'll wait to turn that on until later. This is the power cord, and this screws into my photodiode. So it will take me just a second. It's you have to twist it to get it just right. There we go. And then this screws in. This also has a power button, but I will wait to turn that on. Then I will use this cable to connect my photodiode or my photodetector to my oscilloscope. And there are 3 inputs for this oscilloscope. I'm going to use input A. And then I will connect my oscilloscope to my computer using this USB cable. And if you're familiar with the old printers, this is one of those. It's basically for a printer. So I'll plug in this to here, and this into my computer. And now that that's connected, there is a cap here, and of course I've lost the cap, but you need to remove the cap obviously before you take any measurements. There's also a gain switch, and that's like a zoom switch, and I have this on 0 right now. It's very important to leave that at 0 because you can change it later, but initially leave it at 0 because it will, you can damage the photodetector if the gain is set too high, and I'll show you that in a bit. So first I'll turn the power switch on here, and you can see I've got a green light. I'll turn the power switch on here, and another green light, and you can see, I don't know why they chose red, but you can see in my oscilloscope, oops, that the this camera is totally messing me up, that the light here is red, indicating that it's on. So now that's all the physical components are set up. Now I just need to open the Picoscope software, and I chose the Picoscope 7 early access. The early access could be a little bit flaky, so you might just want to get the regular version, but Picoscope 7 is what I'm going to be using for this, and I really hope it'll open up sooner or later. And you can see that there's a demo device which we don't want, but it automatically detected this other device that I have. And you can see that it is running. There's a lot of controls here, and it may seem overwhelming at first, but there's really just 2 controls that you really need, and I will show you those. The first, and they're ones I talked about before. There's the x-axis, the vertical axis, which is how much voltage output you want to measure, or how much voltage input you're getting, and the other is the y-axis, or the horizontal axis, and that is the time. Here we have, the first thing I'm going to do is we've got plus or minus 10 volts, and this device is not putting out, our photodetector is not putting out anywhere near 10 volts. And so that's why it seems like it's 0. So I'm going to change, I can click on this, and I can change this to plus or minus 50 millivolts. I connected it in. I connected it incorrectly. I put it in the wrong. I'll show you. Oops. Okay, so I meant I should have put it in this A, and I accidentally had put it in this one. So make sure you put it in the A channel. Yep, mistake number one. And we can see that the plus or minus 500 millivolt setting is how much it gets us to the right, so we can see the graph. Let me slow this down. I have this let me speed it up. I've got 1 millisecond per div. Let's change this to 10 milliseconds per div. And now you can see the graph that I had shown you earlier. This is the old-fashioned incandescent bulb that is flickering, but a very gradual flicker. One thing that's confusing, at least was confusing to me, about all these settings for the vertical axis. It seems like the numbers, so that we have plus or minus 50, plus or minus 100, plus or minus 200, plus or minus 500, and so the numbers are getting bigger, and then we have plus or minus 1, and that really confused me until I realized that these numbers here are in millivolts and these numbers here are in volts. And so really this is 0.05 volts, this is 0.1 volts, 0.2 volts, 0.5 volts, 1 volt. So you can see that these numbers are getting bigger. And if you have too small of a setting, you're not going to see any graph at all. But if you have too large of a setting, you can see the graph, but you lose all of the detail. They do have an auto setting, which will automatically choose the right voltage for you for this axis. I don't recommend using it. And the reason I don't is that when the input changes, and maybe there's more light coming out, it will look like the shape of the graph is changing, and it'll be confusing, and you'll think, oh, there's no flickering happening. But what it's really just it's that you just can't see the flickering. It's zoomed out. One thing that now that we have this set up here, we can change the coupling mode here if we want to zoom in on this graph to get a better look at it. If we can change it to AC coupling, and what AC coupling does is it essentially zooms the flicker and puts it around this, makes it kind of like 0, and then that allows us to change this axis so that we can get a much better view of the flickering that's going on. Let me change the coupling mode back to DC. I had forgotten to mention something, and I will do plus or minus 10 volts here. Right now, the photodetector is, you'll have to take my word for it, is about a couple feet from the light source. As I move the photodetector closer to the light source, it picks up more light. And obviously as I move it farther away, it picks up less light. One thing that's very important is that the maximum current that this can handle is, or voltage that this can handle, is about 11 volts. If you put more than 11 volts through this, you will actually damage the photosensor. So it's very important when very important to stay below that 11 volts. And you can control that by how far away the photodetector is from your light source and how bright your light source is. The photodetector has a cool feature called gain, and that's essentially like a zoom. So there are 8 settings all the way from 0 to 70. It's in ohms. So each setting is roughly, for each level, you're roughly doubling the previous one. So this, right now, I have it set to no gain, so no zoom. Now I have 10 decibels, and you can see it's gone up a little bit, and we can see that we're starting to see the flicker a little bit better. This is on 20 ohms, so now I can see that I'm seeing it even better. And I don't want to double it again, because if I did that, I would be close to the 11, and I just want to stay away from that. So this is the highest ohm setting that I want to use to be able to zoom in. Now I can change it to AC. I can change it to plus or minus 100 millivolts. I guess I'll have to do 200. Nope, I'll have to do 500, and I can really get a good view of this this flickering. So let me set the ohm setting back to no gain. So here it's set to no gain, and I want to experiment a little bit with this horizontal axis. So let me change this to plus or minus 50 millivolts, and we can see again a fairly smooth up and down pattern. Now when you compare graphs, you're going to want to make sure that this y-axis and the x-axis are using the same values. So for instance, if I increase this time, it now, this old-fashioned incandescent bulb looks like a very abrupt up and down headache-inducing pattern. But that's only because the time is set to very slow. It's 100 milliseconds per div, so each of these lines measures 100 milliseconds. So this whole screen was painted in 1 second. So although it looks very abrupt going up and down, that's because this time is a large number. As I make this time a smaller number, you can see that it now looks very gradual. This bright down to not bright, and I can stop it by clicking here so I can get a good look at it. So not bright to not bright looks very gradual. Well, that's because this is 500 microseconds, which is 1/2000th of a second. So when you're comparing graphs, you want to make sure that you're comparing apples to apples, and that this axis and this axis, which you've controlled by this number and this number, are the same. So I've got 2 more devices to show you. The incandescent bulb that I've got here and the LED flashlight are both really very simple devices. And so I want to show you a phone that doesn't give me headaches, and then I'll show you a computer monitor that does give me headaches. And both of those are a little bit more complicated, and you'll get some more kind of nuanced results. So what I want to do, so I've turned on my phone, I want the screen to be white. And the reason for that is a white screen is going to give the most light output, and so obviously a dark screen just doesn't produce much light. So I've got my phone on a light screen, and I'm going to take the photodetector and place it directly onto the screen. And I'm going to turn this to DC coupling mode, and then I'll do, why don't I do plus or minus 10 volts. And then I will adjust the gain. So right now I have the gain set to 0, so I'll change that to 10 decibels, and 20 decibels, 30 decibels, 40 decibels. And I'm going to leave it at that 40 decibel mark because I don't want to hit that 11 volt maximum. When I switch it to AC mode, you might say, oh, well, that's nowhere near 11 volts. The 11 volts is what would be measured on DC. So even if you change it to AC, the device is actually putting out, it's not putting out 0 volts. It's just the AC mode is the software that's sort of adjusting it for you. But the important thing for not damaging the device is what does it measure on DC, even if you have it set to AC. So on AC mode, and I'll change this to plus or minus 50 millivolts, this, I'll change it to plus or minus 100 so you can see it a little bit better. This looks like a very noisy signal. But keep in mind that we're zoomed in 40 ohms, or excuse me, 40 decibels, which is, I think, like a 16 times zoom. So let me change it back to 0 real quick. Slowly switching it. So now I've got it set to 0. So when you're not zoomed in at all, it looks like a very, very smooth, non-flickering source. It's just when you zoom in on it that you can see the flickering that much better. So this is now set to the 40 decibels, or the roughly 16 times zoom. And as I reduce this time interval, you can see the flickering a little bit better. So there certainly is flickering coming off of my phone. I'll stop it here so it's not annoying. You can see very jagged upward and downward output of light. But this is 200, those are, excuse me, microseconds. So I think that's 1/5000th of a second. And I guess that's not really the relevant point. The relevant point is that this is a 16 times magnification. So it's not as bad as you might think. This particular device does not give me a headache, even though there is some flickering. So let me show you a monitor that does give me headaches. So I've got the monitor plugged in, I've got a white screen up, and so I'm just going to start over. I always like to start at about 20 milliseconds, and I've got I'm going to turn the gain down to 0, because I don't want to hit that. Turn it to DC mode, plus or minus 10 volts. And I don't want to hit that 11 volt maximum, so I'll adjust the gain slowly. So I have it on the 0 gain is 0. Now it's 10, 20, 30, and 40. And I could probably go to 50, but just to keep it apples to apples with the one that I just looked at in my phone, I'll just keep it at 40. Change this to AC coupling mode, and change that to plus or minus 50 millivolts, and now I can slowly start to decrease the time. And we'll probably start to see a pattern soon. And so here you can see that there is some pretty dramatic up and down flickering. And what I can do is sort of back off the gain a little bit. So I'm at 40 now. Now I change it to 30 and 20 and 10. Is that 10? Yes. And the less gain you have, the more accurate the picture is going to be. So this is 0 gain right here. Is it? Nope. It's 20 gain. This is 0 gain, but it's really hard to see the flickering from there. So if I turn the gain to 10, which is basically a 2x zoom, I can see the flickering a little bit better. As I turn the gain up more, it does zoom in, but you start to lose some detail. And so you don't want the gain to be too high. So so this gain is on 10 decibels. And this does give me a headache. And it took me a long time. I mean, it took me until I had this device to understand why it was giving me a headache, because there wasn't any pulse width modulation, but yet there was still this flickering. And it just seems that this flickering caused a problem for me. And I'm just going to leave all the settings the same and go over to my phone, whereas this flickering did not cause a problem for me. And I can't fully explain why that is. So here's another that really looks kind of like a saw, whereas if I go over here, it looks more like maybe a heartbeat monitor. But for me, this doesn't give me a headache, and this does. And so I've got an apples to apples comparison. And now I know when I'm looking for screens, I can avoid something that looks like this, as opposed to something that looks like that. There are other variables at play, so it is possible there's some other thing that I'm missing. One is a phone and the other is a monitor, so the other one is larger. But it seems that the best information I have is that really, for me, this is the difference. So let me wrap up by talking a little bit about the cost of this equipment and some cheaper alternatives that you might be able to have. This oscilloscope is about $165. I'm not aware of cheaper ones on the market that would work as well. It probably is your best bet, unless you can find somewhere else, maybe a used one on eBay or something like that. The photodetector is kind of the expensive one. That is about $450. There is a do-it-yourself photodetector, and you can see by the electrical tape that yes, I made this. Woohoo! Here's the diode, the photodiode right there, with a 9-volt battery and a resistor, all soldered together. It's really not that difficult to make. You don't have to solder it, and that you can make for like $20. It's not as accurate as the $450 one, but if you're not that sensitive to flickering, it probably is fine. You could certainly start with the do-it-yourself one. The instructions are the same, except there's no adjustable gain. There's no Actually, there is a 10 times magnification. I hadn't thought about that. But it's also not as responsive. It's not as accurate. But I'm extremely sensitive to flicker. If you're only moderately sensitive to flicker, that homemade device is probably just fine. You can always start with that and go from there. All right, that's all I've got. I've got links in the description, and best of luck to you. Thank you.